We'll go live now. We are live.
Good afternoon to everyone of India, and good morning to Madam Professor Gill Reid. It's my pleasure to welcome you all for today's Eminent Scientist lecture. Today, we are fortunate enough to have with us Professor Gill Reid, President-elect, Royal Society of Chemistry, as our eminent speaker. Thank you, Madam. On behalf of the Director CSIR NIST, Dr. Gill Sastry, and the entire SRTP team, I thank you, Madam, for accepting our request to deliver a lecture on the topic New Molecular Precursors for the Selective Growth of Thin Film Metallosulfogenide Semiconductors for Thermoelectric Applications. For the participants of CSIR Summer Research Training Program 2020. Madam, this 2-month Summer Research Training Program was launched on 16th June 2020 by our Honorable Director General CSIR, Dr. Sakarsi Mande, and this is for the first time that we are organizing this program on online platform under the tireless supervision and effort of Dr. Gill Sastry, Director CSIR NIST, so that the young students, especially undergraduate and postgraduate students, as well as the young faculties, will get an opportunity to do science while being stuck at home due to this COVID-19 pandemic. We are delighted that Royal Society of Chemistry is also part of this program, and thanks to Dr. Rajesh Parishwar for his kind initiative. Over 16,000 undergraduate and postgraduate students and teachers from various institutes, colleges across India have registered in this 2-month summer research training program scheduled for July-August 2020. In this program, students currently studying in the BSc final year, MSc, BTech and BE final year, MCA in the final, this both first year as well as second year, and students MTech as well as MPharm, and medical students having excellent academic record, and faculties from various universities and colleges affiliated to UGC, AICTE, state, central, as well as private universities have been considered for online training. Eminent Scientist Lecture is one of the important features of this program, and I am very happy to share with you that this is the 32nd lecture under this series. In addition to the Eminent Scientist talk, we have specialized talk on particular projects, along with that video demonstration of equipments and analytical procedures involved during the experiments are also being demonstrated in the summer research training program. We are very much happy and looking forward to listen to today's lecture by Professor Gill today. With these few words, I once again welcome you all, and before I invite Professor Gill to deliver the lecture, I would like to request Dr. Alok Dhawan sir, Director CSIR Indian Institute of Toxicological Research, Lucknow, to introduce the speaker to our audience. Thank you, and over to you, sir.
Thanks very much indeed. And indeed, it's a proud privilege for all of us at SRTP to have a very distinguished speaker today, Professor Gill Reid. She's not only a president-elect, I think that's the cherry on the icing on the cake, I would say. But before that, she's done a lot of work in the field of chemistry. She has been a professor of inorganic chemistry, and she still is, at the University of Southampton and served as the head of the school between 2016 and 2020. She is born and raised in the central Scotland. Gill obtained her BSc and PhD at the University of Edinburgh before being appointed as a lecturer in chemistry at the Southampton in 1991. She became a professor in 2006. Her group focuses on the research on synthetic coordination on organic metallic chemistry and is motivated by both fundamental studies of new ligand types and explore the influence of metal ligand combinations on properties and reactivity, as well as more application-driven targets. She also works on the development of metal chelate scaffolds for binding the fluorine-18 isotopes, radioisotopes, towards new positron emission tomography imaging, and has published over 350 research articles. She is currently the president-elect of the Royal Society of Chemistry from 2020 to 2022. She previously served as an elected trustee of the Society from 2011 to 2015 and chaired the outreach working group until 2018. I must say at the outset that we are indeed privileged to have an association with the Royal Society of Chemistry for this program, the Summer Research Training Program, which has done fairly well in these COVID times. And I must sort of thank the Royal Society of Chemistry, especially the Indian branch, for supporting us, and also sort of you for accepting this. And before that, we had Dr. Helen Payne also give a talk. So I think it's really enriched our program. And with these few words, I request you to kindly deliver your talk today to the students. They're all waiting to hear from you. Thank you very much indeed. Thank you.
Thank you very much indeed for your very kind introduction. And it's a real privilege and honour for me to join what is clearly a very comprehensive programme of activities, which is really important for the young scientists across India. Never has it been more important that we connect and are able to share training and ideas and network with the scientific community than in the present time. And I hope that before I begin my talk, I wish you all well, and I hope that you and your families are coping with these very challenging times. Thank you for the introduction. I would like to begin by, I'll just share my screen. Can I just check that you're able to see the screen?
Yes, we are, ma'am.
Perfect, perfect. Thank you very much indeed. Okay, so I would just like, before I begin, I would like to just comment that this is the first of the formal duties, if you like, that I've performed on behalf of the Royal Society of Chemistry in my role as president-elect. And I'm absolutely delighted from a personal point of view that this is with the CSIR Young Scientists meeting. I've been very fortunate to collaborate and have friends in science, in chemistry in India, and it seems particularly appropriate, therefore, that this particular talk is the first of these duties, if you like, happens to be with the Indian Society. So thank you for that. In terms of my talk, I would like to spend the next 30 minutes or so telling you a little bit of the journey that we've been on in my group in Southampton in terms of developing molecular precursors, so new compounds, understanding their properties, and then thinking about how we can apply these for new applications in fields of technology. And today's talk is in one particular area, and that is in the deposition, the growth of semiconductor materials for applications in thermoelectric energy harvesting. In terms of the metal chalcogenides, which you see this term up here, what I'm really referring to are predominantly metal semiconductor materials, which are composed of a metal center and predominantly either selenium or tellurium, although indeed sulfur is the third element in this family that form this series of compounds that have these properties. So in terms of metal chalcogenide materials, I'm referring to molecules of this general formula here. So the metal, which would be from the D or the P block, and the chalcogenide, the sulfur, the selenium or tellurium element. And these are binary materials which form structures like the one on the right here. This is a portion of the crystal structure of bismuth telluride, Bi2Te3. And what we can see here, without getting too much into the detail of the structure, essentially these are layered semiconducting materials. The layering is important because we have layers of tellurium separated by a gap and then more tellurium. And these are a little bit like the layers in graphite, where there are individual layers all stacked up on top of each other and weak van der Waals forces that hold the layers together. What that means is that these materials are highly anisotropic, so their properties are very different depending on the direction of the material that you're investigating as a result of this structure. These have a wide range of high-tech applications. I've captured a few of these on the slide here just to give you a flavour. And the one that I'm going to spend most of my time talking about today is actually in thermoelectric generators. And I'll say a little bit about what that means in a moment or two. But they're an important class of materials. There are a wide range of examples. Structurally, they're a bit like graphene or graphite. And the interesting thing is because you've got the metal and the chalcogen and you can vary these, you can tune the band gap, the semiconductor band gap. And of course, that makes the materials more interesting for certain of these application areas. I'm going to be talking about thin film materials in particular. And again, the reason for that is, on one hand, that thin films behave a bit differently to bulk materials. You have greater control over the band gap, and you've got a greater ability to exploit these anisotropic structural properties and functional properties that derive from the crystal structures that they adopt. So the question that arises, I'm an inorganic chemist, my group works in inorganic synthesis, making new molecules, materials, and of course we're interested in, can we bring new chemistry? Can we bring the atom by atom control that a chemist has to create new molecules that would act as precursors for high quality metal chalcogenide thin films? I mentioned that the primary target at the moment is thermoelectric devices, and I thought I should take a moment just to highlight what these are and why they're important and how they work. So thermoelectric devices thermoelectric materials are materials which are based on semiconductors, and they allow the conversion of thermal energy, for example, waste heat from power plants or even from the human body. They take heat, they use the temperature gradient between a hot and cold side and convert that into an electrical potential or a voltage. So essentially they convert heat into electricity, and that's the thermoelectric effect. It's an important effect, and it sounds like it's a fantastic way of capturing waste heat. And why on earth have we not been doing this for many, many years? Well, the answer is that it's not quite as simple as that, because actually the efficiency of this process is not as high as it needs to be widely applicable. But I'll say a little bit more about that in a moment or two. In terms of the types of materials, there are quite a few different classes of thermoelectric material, but the antimony, bismuth, selenide, telluride family are amongst the most promising thermoelectric materials for applications near to room temperature. So from room temperature to maybe plus 100 degrees Celsius. And the key thing is that we need to have couples, we need to have little circuits derived from a combination of P-type semiconductor and N-type semiconductor legs. So this sort of arrangement here, where this would be one thermoelectric material, the N-type material and the P-type material on the other side. And by connecting these electrically in series and thermally in parallel with this temperature gradient, a hot side and a cold side, we can turn that temperature gradient into electricity. And of course, that's the means of creating the power. The diagrams here indicate the sorts of materials that come into this category and just captures a few of the families. I'm not going to spend too much time on this, but just to indicate here in the N-type material, we've got bismuth telluride, and at the same sort of temperature range in the P-type material, we've got antimony telluride. So that's for the room temperature application, combining these two materials is particularly interesting. You can see that going to higher temperatures, wider range of materials are also of interest, but I want today to focus on the bismuth antimony family. Another comment about thin film materials is that if we're thinking about thermoelectric energy harvesting, if we want to use large-scale thermoelectric devices based on something like bismuth telluride or antimony telluride, we have a problem because tellurium is one of nature's lower abundant elements. There aren't large supplies of tellurium. So in terms of having a sustainable energy solution, bulk thermoelectric generators based on the tellurides is unlikely to be a sustainable solution. On the other hand, if we use thin films, we will get less power out, but that means we can focus on particular application areas using these as micro generators, but we use almost 90% less material. So the use of tellurium then becomes viable. And of course, we can think also about more sustainable solutions by replacing tellurium with selenium or some sulfur and optimizing the properties. So there's a very nice review from Schneider in Nature Materials just over a decade ago, which sets the scene nicely in this field. I mentioned the thermoelectric efficiency is not quite as high as we would like it to be. If the efficiency was very high, these materials would have been wide use long before now. The thermoelectric efficiency is normally measured or articulated in terms of this figure of merit term, which is what we call ZT. So ZT is defined by this equation here, and I don't want to spend too much time on it, but suffice to say it applies to some properties of the particular semiconductor material, which we can measure. We can measure the Seebeck coefficient, and then we've got a term here, which is the electrical conductivity. And on the denominator, we've got the thermal conductivity. And one can see that if you can push the electrical conductivity and the Seebeck coefficient up to get high numbers, and you can keep the thermal conductivity low, then the ZT value should be high, and that would be favourable for thermoelectric efficiency. The problem is that the electrical and thermal conductivities tend to increase or decrease together. So if the electrical conductivity goes up, the thermal conductivity also goes up. So that's one of the key barriers to increasing the thermoelectric efficiency. Having said that, there are materials and devices on the market that use these materials and other thermoelectric materials in particular application areas. Obviously, if we can improve the ZT value, then we can make a big impact in the field and widen significantly the applications of these thermoelectric materials to take waste heat from exhausts or industrial plants or pipes and so on to drive Internet of Things type sensors, etc. And one of the strategies, it's not what I'm going to be talking about today, but one of the strategies to do that is to undertake nanostructuring of the material, to dope or alloy the material with other elements to optimize these properties. So that's just a little bit of background to why these materials are of interest in the sort of application area. In terms of the growth method that we're using here, if we want to grow thin films, there are a number of ways that thin films can be grown, but chemical vapor deposition is one of the most widely used techniques. It's used widely in industry because it's relatively low cost. You get fast deposition rate, so you can grow the material fast, and you can scale it to large areas. That's, again, not where we are in this particular project. I'm going to be focusing on small areas for the sorts of thermoelectric microgenerators that we're exploring. But these are some of the common features of chemical vapor deposition that are really important and mean that it's a technique that's used widely in industry. One of the key things is that deposition tends to occur everywhere on the surface. So we would normally say CVD would be a non-selective deposition method. It's got some disadvantages. If you've got high aspect ratio pores, so deep pores in a structure, because the vapor is coming in from above the substrate and having to travel down the pore, what tends to happen is that the vapor contacts the top of the pore, and that initiates deposition and tends to block the pore. So that's often one of the disadvantages of CVD. There are also some variants that one can use, which means we can bring in different target materials and different precursors. And I'm going to be focusing on single source precursors for these sorts of materials. A very simple graphic illustrating the sort of lab-based technique that we use for the deposition, for the low pressure chemical vapor deposition that we're working with. So this box here is a tube furnace effectively. We use a quartz tube which we insert into through the furnace. At the far end on the right here, we would place the precursor in a little precursor bulb, and then we would place our substrates along into the hot zone. We connect this up to a vacuum system so that we can take the pressure down to around 0.1 torr or maybe a little bit lower. And then we can adjust the temperature to achieve the deposition, obviously dependent on the precursor and the target material that we're working with. So that's the broad method that we use to screen our molecules. There's lots of CVD equipment for manufacturing scale on the market. So we test these materials in this type of approach with a view to scaling to wafer scale. And that's something we work with our collaborators on. So something about the precursors, and moving on to the chemistry component then. So I'm referring here to using our chemistry to develop single source CVD precursors. And what I mean by that is single molecular species that will incorporate the elements that we want to put into our deposited material, our metal chalcogenate material. These elements would all be contained within that single molecular entity. So we only need to use one metal compound for the deposition, but we've got to obviously design that carefully so that we can move it into the hot zone and drive the deposition process so that we achieve the level of control that we're looking for our thin film material. Usually we have direct bonds between the bismuth and the selenium or tellurium or whatever else it is that we're using. And by using a single source precursor, we're often have an advantage that we have easier handling because the coordination environment around the central metal is completely filled, so that reduces the likelihood of air or moisture causing degradation, or indeed many other dual source precursors that are used in CVD can be pyrophoric, highly moisture sensitive and so on, which makes handling more difficult. One of the key things that we've been exploiting is that by choosing the right single source precursors, we can get much better control of the deposition parameters. And that means that we can control the stoichiometry, so the ratio of the elements in the material that we're going to produce. We can also, and I want to illustrate to you today, that we can get really good control over morphology and also the dimensionality of the deposited materials. And these are some of the advantages that we want to use for our micro devices in this project. It would be unfair to say that single source precursors answer all the questions. They have some disadvantages. And just to be fair, the disadvantages are that clearly by incorporating everything in a single molecule, the molecular weights are higher. And so that tends to lead to lower volatilities, which is why we are often using a low pressure process, although there are other methods, liquid injection, CVD and so on, that are perfectly compatible with these sorts of precursors. We've also got to think, if we want to scale this for an application of wide use, then we need to keep the synthesis cost. The cost of producing the precursors must be kept down, otherwise it becomes non-viable. And we also need to think about the deposition pathway so that we can avoid incorporation of impurities into the material, which would obviously compromise the properties. So these are the things that are in our mind when we're thinking about this. So the sorts of complexes that we've been working on really derive from, and maybe this is one of the key things that I'd like to emphasize, is the progression from fundamental research to application-driven targets. We started in this area working on developing new coordination chemistry, just exploring fundamental aspects of the coordination chemistry of these chalcogenoether ligands of this type, where we've got a chalcogen, sulfur, selenium or tellurium, and two R groups, which might be alkyl or other organic groups. These are relatively modest sigma donor ligands to acceptors, to metals and metalloids. We've also looked at the anionic derivatives, the chalcogenolate ligands, which offer different properties. These are now obviously charged ligands. They're more covalent interaction between the E atom, the chalcogen, and the metal center. They have some advantages and some disadvantages. We've also, in these explorations, clearly, and I should say there's been a lot of very nice work across India in a number of research labs looking at this area of chemistry. It's an area that's got a strong heritage in India, but the electronegativity of the chalcogen decreases as we go down the group, and equally the carbon to chalcogen bond strength in these sorts of ligands tends to get weaker as we go down the group, so the tellurium carbon bond is rather more easily broken than a sulfur carbon bond, and for a deposition process that's something that could be quite advantageous. So, as I say, we're interested in looking at complexes of these sorts of ligands with main group acceptors to create new molecular single source precursors. And these would normally be neutral complexes. And so we're often going to be using P-block halides, the P-block main group chlorides, for example, which tend to be modest Lewis acids. So that's compatible with our basic ligands. The P-block halides themselves are oxophilic and often readily hydrolyzed, so we need to think about our handling conditions, so using inert atmosphere, nitrogen or argon atmosphere, so using vacuum lines and glove boxes for the synthetic part. We've also got to think about our solvents and the conditions that we use for the reaction chemistry to form the complexes, because if the complexes are relatively fragile or relatively unstable, which on one hand is desirable for the application, we need to be careful that we don't drive that decomposition in an uncontrolled way. So we need to think about using weak donor, non-competitive solvents. We often use things like dichloromethane or acetonitrile as a solvent, and often room temperature or low temperature conditions. It's worth just commenting that prior to that early work that we did, complexes of the main group elements with tellurioether ligands in particular were extremely rare. And I want to show you today that by developing that fundamental chemistry, we've been able to evolve it forward into applications and some success in this area. So here's the first sort of example of a precursor that we've made, and this was actually made at a time when a young Indian scientist, now an academic in Mahindra University in Hyderabad, Chitra Gurnani, was working in my lab in Southampton. We've collaborated for a number of years, and it's always been a really stimulating time. I've thoroughly enjoyed working with Chitra. She's a really excellent scientist. And Chitra worked on this molecule. This is bismuth trichloride with these butyl telluride ligands coordinated. This is a red oil. It's formed in very high yield from the scheme shown above. And the red oil tells us it's got some vapor pressure. And by looking at the thermogravimetric analysis, we can actually see that under these conditions, that as we increase the temperature, we drive mass loss. And the final stable mass that we end up with is fairly close to the mass we would expect for Bi2Te3. And so that gave us encouragement that this precursor might be a good reagent for CVD experiment. So we went on to look at that CVD experiment using the equipment that I've shown you. And you can see from the scanning electron micrographs here that we actually do see very nice coverage of Bi2Te3. This is polycrystalline material. We can see that coverage is very nice, and we've got what looks like quite highly oriented. This is a rhombohedral structure, so these are hexagonal platelets or rhombohedral platelets which are lying flat down on the surface of the substrate. We can track the characterization using here Raman spectroscopy, and this is a characteristic Raman spectrum for Bi2Te3. Importantly, we can establish from a range of techniques, including energy dispersive X-ray analysis, we can see that we have no chloride incorporation. So all of the chloride that was in the precursor molecule has been eliminated in the deposition process. And we have what appears to be very nice quality N-type semiconductor material of Bi2Te3. So that was a very encouraging situation. We then went on to look at, if we want to make these thermoelectric devices, then we would like to be able to deposit our materials in particular regions on our substrate, on the material that we're depositing onto. And so we've used patterned, lithographically patterned substrates, which by doing this, what we have is the blue area that's overriding this is silica, which is an insulating surface. And the yellow areas there are a layer of titanium nitride, which is a conducting surface, which sits at the bottom of this material. Sorry, of this trend, this recess. And what we've been able to show is that by using this single molecular precursor, rather than combining lots of different things in a CVD reactor, that we get a really high level of discrimination between silica and titanium nitride. And I'm illustrating that. I hope you can see the colors okay, but the SEM image here shows the deposition into two of these adjacent recesses, and you can see the material at the bottom here. And then we can do the EDX mapping to look at the composition, and it's very clear that the bismuth and tellurium are only occupying the regions where the film has grown on top of the titanium nitride. So this is unusual for CVD, that we're getting this very high substrate selectivity, and you can see that reflected in some of the figures at the bottom, just showing that you get really beautiful arrays, quite unexpected degree of selectivity by controlling the quantity of precursor we use, so that we supply enough just to fill the titanium nitride region and not to coat the insulating silica region. We've been able to take that further and show that we can control the orientation of the crystallites within these recesses. So again, this is an SEM image of a little 1.5 micron diameter well that's been created. So the dark grey is just showing some titanium nitride. This region outside is the silica, and we can see the bismuth telluride crystals growing beautifully within the titanium nitride region. And you can see that the platelets are lying flat down on the surface with the C-axis of the structure normal to the substrate. If we take the lithographically defined recess diameter down, so this is now down to 200 nanometers, what we do is turn these crystallites up on end, and now we have the C-axis parallel to the substrate. So we get a remarkable degree of control of the orientation of the crystallites as we control as we define the substrate underneath. And that's illustrated in this graphic at the bottom here. So that's a very nice situation for bismuth telluride. Around the same time, we were thinking about, well, we need both an N-type material and a P-type material. Bismuth telluride's a perfect example of the N-type material. For the P-type material, we want antimony telluride or antimony chalcogenide materials. And so in this case, we've used, in the example here, I'm showing you using a chalcogenolate complex. And so this is an organometallic compound with a methyl group on the antimony, 2 chlorides, and we can do a salt elimination reaction using chemistry that's well established now in this area, and form these organometallic or covalent interactions between the antimony and the selenium or tellurium. These molecules are quite volatile. Again, they're oils, they're air sensitive, mainly to moisture rather than oxygen itself, and they form in very good yields. And at the bottom of here, I've just shown you that the same principles that we saw for the bismuth telluride work beautifully in this antimony telluride system. So we can see that we can fill circular recesses, we can control the orientation of the crystallites, and we can also fill trenches to create what would ultimately be, for example, the legs, the individual elements of a thermoelectric device. So we can create arrays of these lines which are fully filled with antimony telluride to give the P-type material. We've looked at the thermoelectric properties of these materials, and I want to acknowledge the significant collaboration and very enjoyable collaboration that we've had for a number of years with my colleagues in electronics and computer science at the University of Southampton. One of the enjoyable things about working on a project like this is that we can bring our chemistry expertise and that ability to create molecules and control deposition and orientation, but working with experts in areas like at the electronics side, we can undertake these sorts of studies where we can really look at the functional behaviour. So this is looking at the Seebeck coefficient as a function of temperature here, and you can see very clearly where these materials have their maximum. And this is showing that as we deposit these materials at different temperatures, we see quite a variation in the Seebeck coefficient, which is going to be important in tuning and optimizing the thermoelectric generators that we're producing. Indeed, these are P-type semiconductors, and that's clear from the data. And if we work this through, we can anticipate a maximum ZT value of about 1.3 for the film undertaken at the lowest deposition temperature. I should emphasize that that's taking account of the electrical conductivity. Measuring the thermal conductivity in thin film materials is still a very challenging process. We have some data, but we're still working hard on that to really pin that down. So we can produce bismuth telluride and antimony telluride, but one of the key things that we would like to be able to do is optimize these thermoelectric properties by doping in some selenium into the bismuth telluride material, or some antimony into the bismuth telluride, and so on, to create these ternary materials where we get a control of the nanostructure within the interfaces between the crystallites, which has been shown to make a big difference in terms of the measured thermoelectric properties. And the approach we've taken here is again using what I would say is our underpinning chemistry, molecular chemistry, rather than an engineering approach. Here we're taking our precursor that we've seen already that produces bismuth telluride. We can make the corresponding bismuth selenide precursor, and because these are neutral ligands and only bind weakly to the bismuth, if we combine these in various ratios, we can cause exchange between the tellurium and the selenium ligands. And in the example I've shown here, by taking 2 equivalents of this molecule, tellurium, and 1 equivalent of the selenium, we can produce effectively this species here, where the ligands are rapidly exchanging, but on average, we now have a precursor which contains bismuth, selenium, and tellurium in a single molecule. And we can do CVD with that. We can use this in a similar approach and generate these ternary phases where we have a variation in the selenium or tellurium ratio depending on how much of each of the precursors we use. And again, just to illustrate this in terms of the structures, depending on the composition. So we've got the two, we've got the 2 extremes. This is bismuth selenide, the binary material, and bismuth telluride, the other extreme binary material. And then we can see that we're just showing some examples of different ternary compositions within that. If we look at the EDX analysis to get the composition, we can see that the bismuth content remains pretty close to the 40% that's expected, and we can vary the selenium and tellurium content according to the ratios that we put in. So that gives us a really excellent way of generating precursors that can give us the ternary materials. And if we look at the diffraction data, and again, this was work that was done in collaboration with Dr. Chitra Gurnani, what we can see here is that we've got very nice solid solutions from the X-ray data. Instead of seeing where we have the mixed precursors going in, what we're seeing is a single, if we just focus on the 015 reflection, you can see that that moves smoothly with composition, which is a good indication that we have a well-distributed solid solution. What that means is that we've got the bismuth telluride structure, but we have some selenium sitting distributed through the lattice, sitting on the tellurium sites. So that's exactly the sort of scenario that we were hoping for. Again, we can use these to deposit these ternary films, and without going into the details of the thermoelectric measurements here, probably the most important thing to say is that we can generate N-type materials with a range of compositions, and we can see a variation in the thermoelectric properties, so we can optimize the thermoelectric properties based on that composition. And this work has actually just been recently published in the literature. So I hope that that's given a sense of how we can do this chemistry. What we're trying to do and what we've been working on more recently is now putting these into a device type structure, using this line, using lines of these materials to create the P and N type legs. So this is just a graphic showing our molecular species, where we would have conducting surfaces in some of these areas, and we would have cleared these, unmasked them to create regions where our molecules will deposit, so to expose the titanium nitride. And on this figure down here, we can see the black region is actually bismuth telluride on what was the exposed region. We will then mask that off, cover it, and unmask the next tinitride region to deposit the antimony telluride. And then we have these arrays shown in the cartoon graphic here of P and N couples to generate our micro device. So that's really what I wanted to say about the thermoelectric materials, and I hope you can see how this can evolve and different materials can be brought in. I just wanted to finish with a couple of slides showing a different aspect of the metal chalcogenide chemistry, just again to illustrate a little bit of the versatility of the using these molecular precursors and other molecular precursors, but these single source precursors to drive the deposition of interesting materials for nano electronic applications. And I would start by, again, going back to an example that we did, well, we published in 2012, and this was work that Chitra did when she was in her fellowship from the Royal Society working in Southampton. This is a tin chloride complex with this diselenoether. It's a very simple distorted octahedral molecule. It's neutral, it's an oil, it has some volatility, and in a low pressure CVD experiment, we can deposit SNSE2, so tin diselenide, in a very nice manner with control over the orientation of the crystals, depending on whether we have thicker or thinner samples. And we can do that by controlling the quantity of the precursor. And then over on the right here, we have the selective deposition into these pattern substrates. And again, you can see very clearly that in the region where we've got titanium nitride, these yellow circles and squares, that's where the tin selenide is depositing. We've looked at the performance, the electrical performance of these films, and they're comparable to films produced by molecular beam epitaxy, which is one of the best, the highest quality benchmarks for semiconductor materials. So initially we were using these to deposit thin films, and tin diselenide has got a range of interesting applications. But it turns out that if we increase the temperature, we can also deposit the tin monoselenide. And we've collaborated with colleagues in the University of Cork, Justin Holmes and his team in Cork in Ireland. We've been working with him to use our precursors in a liquid injection CVD experiment. Now, in this case, we're using gold nanoparticles on a silica substrate, and we're using a toluene solution of the precursor. And what we're able to do is, depending on the deposition temperature, we can grow arrays of these tin monoselenide nanowires. These nanowires are depicted in the transmission electron micrograph at the top here. What you can see is we've got quite nicely defined tin selenide nanowires. You can see the gold seed at the end of these nanowires, and we can follow this by Raman spectroscopy and look at the X-ray structure and so on. If you take the temperature up a little bit, you change the direction of the growth. You go from a 011 growth direction, which is the figure at the top, to a 100 growth direction, which is the figure at the bottom, just by changing the growth temperature, which is, again, I think the point really to emphasize is we're getting a remarkable level of control, way beyond the level that we would have anticipated when we started out in this project, that we can control orientation, growth direction, the one-dimensional structures, obviously, and the two-dimensional structures that we've seen already. And these nanowires we've been looking at, we've done some preliminary experiments, which was recently published, looking at these as for applications in resistive solid-state memory, so resistive RAM for nano devices there. And we see very promising data with on-off resistive switching ratios of about 10 to the 3, which is pretty competitive. So that's showing the growth of these nanowires using the same sort of molecular precursor. And the last example to show you is using, again, the same precursor, but slightly different conditions. Now we can grow these nano networks. So these are like sheets, like thin films, where we've got ribbons which are crisscrossing to create these nano networks. And you can see they differ across A, B, and C in these images, the scanning electron micrograph images. And these are just controlling the growth as a function of the precursor concentration. The morphology here is particularly open. These are really very open structures with not many tins and seleniums in each portion of the structure. And SNSE, tin monoselenide, is an interesting material, like many of the chalcogenides, for new anode materials in battery applications. And we've done some preliminary work, and this has been in very much the collaboration with Cork, looking at these for intercalation of lithium ions for lithium-ion batteries. And what we find is, again, it's fairly early days with this work, and we've obviously got more work to do. But because we've got this very open structure, we retain very high capacities after multiple cycles. So after this sort of 50 cycles, a bulk material or a film would be decaying down to maybe 40% capacity. We're seeing retention of high capacities because of the open structure, because as the lithium goes in and out of the layers, so the idea here is that you've got these layers with the layered chalcogenide, and the lithium ions can intercalate between the layers. Obviously, when the metal ion goes in, the layer has to expand a little bit, and as the lithium ion comes out, it contracts a little bit. And if you imagine that over many layers, you extrapolate the expansion every time you put another layer on, and eventually you start to get breakdown of the structure. If with only a few layers, what we see is that the molecule can breathe as the lithium ion goes in and out, and continue to do that for extended periods. We're also seeing quite high specific currents under these conditions. So I hope that that's illustrated a different sort of application area for this sort of chemistry. So just to finish, what I hope I've been able to share with you is really from a chemistry perspective, the control that the thing that the chemists have that is maybe different from other sciences is the ability to manipulate molecules on an atom by atom scale. And by using our control of that chemistry and our skills in that area, we can make and explore the properties of new materials, new molecules. And that's very much at the heart of this project. We started by making these chalcogenoether complexes and chalcogenolates just as a chemical curiosity to see whether we could make them and how they would behave. And over time, we've begun to understand some of the properties and exploit some of the features to be able to get this collaboration and the ability to grow these chalcogenide materials with, I think, what is, I hope you agree, a very surprising level of positional, orientational and morphology control of the material that's being deposited. And that's really important for high-tech applications. There are many areas of in nanoelectronics and optical materials and so on, where the ability to get control of dimension with high quality materials is really critical and will be, I think, the breakthrough areas for the next generation of these sorts of materials. As I say, I've illustrated it for thermoelectric materials. You can see that you can combine these, again, by thinking about the chemistry a little bit, you can combine these to be able to optimize ternary and higher materials. And by using these molecular entities, we've got this substrate selectivity, which allows us to go into prototype devices. And that's very much the area that we're working on the thermoelectric project now. The VLS type growth, the nanowires and nano networks, opens up many new opportunities, and that's a really exciting area that we're hoping to exploit going forward. So I'd like to finish by, of course, acknowledging the people who have done this work, and I won't go through everybody on this list, but in chemistry in Southampton there have been some key people, my colleagues Bill Levison and Andrew Hector, that I've worked with for a number of years. We collaborate closely together, and each brings their own area of expertise. And I think that's a really important part of a collaboration, is you bring together the various parts of to solve the problem that you're trying to tackle, and that's been really, and it's also got to be fun. You've also got to enjoy working together and so on. Sophie was a PhD student and postdoc in my group. She's now an academic in Nottingham Trent University. Vicky and Stephen were postdocs on the CVD grant on the thermoelectric project, and PhD students Sam, Fred and Ellie. In electronics, the key people really have been Kees de Groot, who's a specialist in nanoelectronics and has been able to help us to focus on maybe the more interesting challenges from the application side. And I think that's been an important drive in terms of our chemistry. Romeng Huang started off doing a PhD with Kays and ourselves on a completely different project on phase change memory by electrodeposition. He is now an academic, a lecturer in electronics and computer science in Southampton, and is really an expert in thermoelectric devices. So that's been great. And probably the two key collaborators in terms of our external collaborations have been Chitra, whom I mentioned already. Chitra, we still collaborate through Chitra's Royal Society Newton Fellowship. She's a Newton alumnus, and of course she is now an academic in Hyderabad. And Chitra's made huge contributions in the earlier stages of the project. And more recently, Justin and Soba at the University College Cork, working on the nanomaterials. So with that, I'd like to thank you very much for your time today. Thank you for joining, and I'm more than happy to take questions. Thank you.
Thanks very much indeed.
Thank you very much.
And now I'll request Dr. Sekia, go ahead. You can ask
Yes, sir. Thank you very much. Yeah. So thank you very much, madam, for the wonderful talk. And you have touched upon, starting from the how this, P-block chalcogenide can be used to develop, high-quality chalcogenide films, nanocrystals, nanowires, and nano networks, and how this binary and ternary, these chalcogenides can be very good material for thermoelectric applications. Really, it's a wonderful talk, and you have touched upon the many, techniques like liquid injection, CVD, and all. I think all of the participants are highly benefited from your work, from your talk. And we look forward to hear from you. Before going to the question answer session, now may I request Rajesh Parishwar sir to say a few words. Over to you, Rajesh sir. Sir, you are mute, I think. Please unmute, sir. Rajesh.
Hello, can you hear me?
Yeah, sure. Please go ahead. Yeah.
There's some problem with the connectivity. No, I wouldn't say many words. I think there's a big question answer. I saw there are lots of questions here. Just I would like to thank CSIR for giving us opportunity to collaborate on this SRTP program, which is kind of very unique as well as very interesting way of delivering the summer training programs in this unprecedented times. And I think we've had a wonderful collaboration over the last 7 to 8 weeks, and I think hope we continue with a couple of more programs in future as well. Thank you once again. Thank you, Gill, for being part of this program and delivering an excellent lecture. I think students would really love to go forward and look at what are the new opportunities for them to research as well. I think that's, and I know there are a lot of questions, so I'll just close here and we can proceed with the Q&A session right away.
Thank you, Rajesh Parishwar sir. And now I would like to request Lisa and Monty for the question answer session. Over to Lisa and Monty.
Thank you, sir. On behalf of our director and the entire CSIR SRTP team, we thank you, ma'am, for your insightful and very informative lecture. There are lots of appreciation in MS Team, YouTube, and Facebook for your lecture, ma'am. All are appreciating it. And we have lots of questions, but we have selected few of them. So if you permit, can we ask you, ma'am?
Of course, yes, please do. Very happy.
Thank you, ma'am.
Thank you so much, ma'am. So the first question is, sometimes by using CVD method, thin film does not get uniformly deposited. And what will you suggest regarding this, ma'am?
So I think that's absolutely right. And of course, the choice of precursor will be a key decision point in terms of improving the precursor will tend to give better coverage. I think the other thing, the other advantage of chemical vapor deposition is that there are a number of different techniques that one can use. So I illustrated two. On one hand, where we heat the precursor and carry it over in a vacuum across the substrate, and that's one way of moving the precursor. But in the tin work, we've also used liquid injection. So you have the ability to dissolve the precursor in a solvent and then apply effectively an aerosol and remove the solvent, but to deliver more uniform coverage of the material. So there are various techniques in chemical vapor deposition that give rise to that. But of course, the nature of the precursor and the nature of the substrate that you're depositing onto are probably the two main factors that are important.
Thank you, ma'am. And our next question is from Revati. She is saying, in comparison with tellurium, selenium is somewhat toxic. In such cases, how could we do laboratory chemical reactions safely?
So I think the important thing to be aware of in terms of the chalcogens is that it depends very much on the nature of the molecule that the selenium or tellurium is in. So it depends on how you bind that within the ligand type that we're using and the complex. So for example, you know, we tend to use these neutral molecules, the selenoethers or tellurethers. They're somewhat, particularly the tellurium compounds, are somewhat air sensitive. They have some volatility, but they're not particularly volatile. And so we tend to use extraction systems. So these could be done in a fume hood, or even a glove bag is satisfactory for handling these. Obviously, if you change the nature of the terminal group on the chalcogen, you change the chemistry again. So molecules like H2SE or H2TE are particularly toxic, both because they're volatile and because the tellurium or selenium to hydrogen bond is very weak. And so we would breathe them in and they would react and cause the toxicity. So again, it comes back to, I would suggest, the choice of the precursor molecule to both reduce the toxicity, but also to make sure that the deposition process is clean and that all the organic entities that are in our precursor molecule can be pulled off cleanly so that they don't get incorporated into the film. Thank you. I hope that answers the question.
Thank you so much, ma'am. So the next question is from Dr. Rohini. Can single source precursor route is equally effective in depositing thin films of bismuth telluride or antimony telluride using vacuum evaporation route? Also, can there be same be applied for mixed metal chalcogenides?
So I think I very much believe that the method for the deposition depends on the application that one wants to use the material for afterwards. So in our case, we're really there are very few deposition techniques that give the control of where the material deposits. What you would tend to have to do if you're using physical vapor deposition, for example, or more conventional precursors for chemical vapor deposition, would be a series of deposition and then etching steps. And all of that these are additional processing steps which are expensive in terms of the effort and the equipment, and it's also expensive in terms of the material. There's a lot of wasted material. I think the reason that we've focused on the chemical vapor deposition for the chemistry that I've talked about today is that we see this ability to exploit the substrate discrimination to get area selective deposition. That there's probably the only other technique that really does this well is electrodeposition, where in electrodeposition methods you deposit the material only on the conducting surfaces. So by using the single molecule precursor here, we're seeing a degree of control where the material can be deposited that we wouldn't normally see with many of the other deposition techniques. Thank you.
Thank you, ma'am. The next question is from Dr. Goswami. He is asking, how can we prevent oxidation during deposition?
So that's an important point indeed. In our deposition system, we're using a vacuum. So we would tend to transfer the precursor into the precursor bulb in maybe a glove bag or a glove box under an inert atmosphere. And then we connect that up to a pump to evacuate the tube. So we have, initially we're manipulating the precursor in an inert atmosphere, then we take it under vacuum, we carry out the deposition, when we switch off, when we stop the deposition, we refill with nitrogen, close off the reactor, let it cool, and then take it into the inert atmosphere to release, to unload the samples. And we tend to store them in a glove box. But actually, we don't see a lot of degradation of the surface. The worst problem we tend to have is if we get moisture in the early stages, we tend to get oxides forming through hydrolysis, and that gets incorporated into our film. And obviously, that's not a good thing. So we tend to just work under inert atmosphere, so under nitrogen. It depends. Some precursors are perfectly air stable. And so you wouldn't need to worry about that in the same way. But there are ways of doing that to eliminate the probability of oxide on the surfaces. Thank you.
Thank you, ma'am. There are actually lots of questions. So if you don't mind, can we ask you one last question, ma'am?
Please, yes, of course.
Thank you, ma'am. So the next question is, suppose we have a prepared thin film, but immediately it is not possible to go for characterization. Then for that period, how could we protect the film for a larger time? Could you suggest some ways for it, ma'am?
So the key that our normal way of doing this would be to carefully transfer the film from the tube that we're doing the deposition in, using tweezers, not using fingers or gloves because you tend to contaminate them. We tend to use tweezers and just lift them with the edges. We would then put them into little plastic boxes that we would store in the glove box. So the box would be closed essentially in a nitrogen or argon atmosphere, just an inert atmosphere. We try to characterize the materials as soon as possible after deposition, but we've also done repeat checks to make sure that we know how they behave over time. Mostly we see very little. You might get some surface oxidation, but quite often it's a very thin layer on the surface and it doesn't affect the properties significantly. If we're putting these into devices, then obviously we'd be doing the deposition and then covering the top surface anyway. So we would be enclosing the material inside the device structure, so we can eliminate that degradation process that way. You can get things like vacuum containers that you can put samples in. We haven't gone to that extent. We've not found it necessary to do that, but it's a solution for some materials which are particularly sensitive to oxygen. Thank you.
Thank you so much, ma'am, for nicely answering all the queries. It was indeed a pleasure for all of us to hear from you, ma'am. And all the participants are enlightened hearing your lecture, as we see lots of comments for you, ma'am. So, ma'am, we look forward to hear more from you. And this is all for the question and answer session. Now I would like to hand over the session to the next fragment of today's program.
Thank you, Lisa and Manti. Now I would like to request Dr. Alok Dhawan sir to say a few words. Sir, please.
No, I think they summed it up very well. I think the good questions that students have asked. It only goes to show how, in simple words, Gill has been able to explain the very complex work that she's been doing on these nanomaterials. So I think it's very well accepted in the community today. And I would once again thank her for taking out time and sort of sharing her experiences with us. Not only the students, but also the young faculty who are on this live broadcast would have benefited immensely. Thank you very much indeed, Jim.
Thank you very much. It's been a real pleasure. Thank you for the opportunity.
Thank you.
Thank you, sir. And yeah, thank you, Professor Gill, for the wonderful talk. Now, I would like to request Dr. Ravi Kumar Lingam to offer a formal vote of thanks.
Thank you, Dr. Lucky. I, on behalf of Director CSIR NIST and entire CSIR SRTP team, and on my personal behalf, I extend my hearty thanks to Professor Gill for the wonderful presentation on the thin film metal chalcogenides. And thank you very much, madam. And you covered the importance of these thin film metal chalcogenides in technologies like thermoelectric energy harvesting and solid state memory and this and also the materials of batteries like this tin selenium networks and tin selenium nanowires, how they are playing a vital role in solid state memory and also this as an anode material in lithium ion batteries. Thank you very much. And I profusely thank Dr. G. Narahari Sastry and Director CSIR NIST and Dr. Alok Dhawan sir, Director CSIR IITR, for guiding us and to make this program more vibrant. Thank you very much, sir. And I thank Dr. Rajesh Parishwas for connecting us to the host of distinguished speakers. Thank you very much, sir. And I thank all the participants who are joining us today through the MS Teams, YouTube Live, and Facebook Live. And thank you all.